Hello, this is Mr. Gilmore with the 11.1 Square and Rectangle Area. So today we begin a new chapter investigating area. And so where we actually begin with area is first talking about the definition of area. We'll then move into three postulates related to area, and then we'll prove our very first area theorem, which is really an area formula, and of course, what would be left out if we didn't have a partridge in a pear tree. So let's dive into talking about area. So we start with actually the unit square. And why we start with the unit square is because this is going to essentially be the cookie cutter that we're going to be using to chop out area of a given figure. See, we can actually measure area using different shaped cookie cutters. We could use a unit circle. We could use a unit triangle. We can use many different unit objects, unit figures, as we begin measuring area. But the typical area measure is using the unit square. And the reason why we use the unit square is because the square is really nice to us. It has such good properties to it. We've got those four right angles, four equal sides, and again, it offers a lot of information for us that makes it useful as one of the most ideal cookie cutters that we're going to be using to define what area is. So simply, what is a unit square? It's simply a square with the side length of 1. Now, 1 what? Typically, we assign a unit of measure that applies to that value of 1. But really, the units of that 1 are arbitrary. It could be any sort of unit. It could be meters, inches, light years, parsecs, you name it. It does not make a difference because no matter what size figure we're dealing with, we can adjust the units of our unit square to also then adjust to the size or shape of the given figure. So units are arbitrary. We will be essentially finding that we are able to calculate the area of a given figure without the need of knowing what the unit or the dimension of said figure is. So now we move into the definition of what area is. The area of a figure is the number of unit squares needed to cover it without gap or overlap. So imagine you're given a figure and you have your cookie cutter of the unit square. You are then going to stamp out as many of those squares from the given figure without gap and without overlap. Because if we overlap, then our number is too much, right? We've counted too much area. We've counted too many of our unit squares that are needed to cover our figure. But if we leave gap in between our cookie cutters with our unit squares, then our number is too little. That means we haven't counted enough area, the area that would cover our figure. Let's take a look at an example of a figure that we can actually count the number of unit squares that we can chop that figure up. So let's say that we've got this grid already placed for us where each of the squares we see is a unit square. And we can see that as I have the two axes labeled as you see going from the center or the origin of these axes along each of the grid lines, we find our unit squares. So we've placed a rectangle into the diagram, or into this plane, where this rectangle, we have then the ability to count simply the number of unit squares that fit or cover this given rectangle without gap and without overlap. And so we count, we find that we have found 8 square units, 8 unit squares that are then filling or covering this rectangle. So then by definition of area, we can simply say that the area of this rectangle is 8 square units. That is what we find that rectangle to be. Now we're going to be moving on to our postulates, and you know the drill, right? Once we experience our initial definitions, we want to see how our definition then begins to interact with any given figure, especially with any figure of an area. Now, our postulates, I do want to make sure I impress upon really the obviousness of these postulates, and they really are obvious. And so we're going to find there are 3 postulates that are going to lead us into our very first discovery of our very first area theorem that we'll encounter in this first lesson. So we start with the area addition postulate. Basically, imagine given a certain area or certain figure. We could then take that figure and divide that figure up into several different sub-regions. What we then find is that if we know the area of all those sub-regions, we then may add those sub-region areas together to then equal the area of the whole region. So essentially, this is something that we have seen really since the beginning of our system, but way back in chapter 1, that the sum of the parts is equal to the whole. So the sum of the parts of the area is equal to the whole area. And that should be pretty obvious to us. That in our example here, we've got this pentagon, and let's say that A is the area of the pentagon. That means the area A is equal to the sum of those three subregions, A sub 1, A sub 2, and A sub 3. And those three then together make up the area of the whole thing. Now let's take a look at the area congruence postulate. This is also one that's pretty obvious. That if two figures are congruent, then their areas are equal. So here's a quick example. If we're given two pentagons that are congruent, then their areas will be equal. When we think back to our definition of congruent, we made a list of the um, polygons information. We made a list of its angles and sides. But we could also add to that list the measure of its area. And that means we're going to find that in that list that where those corresponding areas match up, they will be equal in measure. The last area postulate that we have for today is the square area postulate. That if we're given any square that has a side length s, then its area is simply s squared. And this should be pretty obvious, that when we take the side length of a given square, no matter what that side length is, imagine then we have our unit square as our cookie cutter. If we're chopping squares out of a given square, then we simply will then find that the number of unit squares that we can chop out of that given square is then the side of that square squared. So we have s squared being that side length, and of course we can adjust our cookie cutter to really any dimension we need so that we can find then the number of unit squares that it takes then to cover this given square without gap or overlap, and it will be pretty obvious then that the area or the number of those unit squares will equal s squared of that given square with side s. So with that square area postulate, let's do some quick examples then of finding the area or being asked to find some information about a given square. And we're going to find in these examples that our area, we can find it really given a number of different pieces of our square, and we could still find the area. So let's start with our first example here. A square has a side length of 2. Find its area. Well, if we want to, we can go ahead and draw a quick diagram of our square here with a side length of 2. And what that leads us to is using our square area postulate to say that the area of the square is simply then the square of its side length, which then leads us to conclude that the area of this given square is an area of 4. That means we would be able to chop 4 unit squares out of that given square. Now let's move on to our second example. A square has a diagonal of length 2. Find its area. So our diagram changes a little bit. I can't place the 2 on the side of our square, but I can place the 2 on the diagonal of our square. Now remember, diagonals are really important to us in squares because diagonals bisect the opposite angles, which then means we are dealing with a 45, 45, 90 right triangle. So we have to recall our information about the 45, 45, 90. We are given the length of the diagonal, which happens to be the length of the hypotenuse. And so we can work backward from the length of the diagonal to find the length of the leg of our 45, 45, 90, which just so happens to be the side length of our square. So I take 2 divided by root 2 to go backward, and simplifying that, we get a side length of root 2. So we find then the area is really then the square of the side of that. Now when we square a square root, those two will cancel each other out. They're inverse functions. And what we're left with is just simply the number on the inside of our radical, and that means we find the area of our square to be a length, or the area to be 2, which means in this given square, using our unit square, if we were to then think of our unit square with a side length of a half, it would then take 4 of those, and we then remember if we adjust it from a half, half of 4 would then be 2. Now the last example, a square has an area of 25. Find the length of its diagonal. So now we think of our area equation here to work backward. If we're given the area, we can actually then work backward to find out what the measure of the side is. So we plug 25 in for the area, and then think, how do we solve for s? We simply take the square root of both sides. So taking the square root of both sides results in the square root of 25, giving us 5. So there is the side length of our square, but then it asks us to find the length of its diagonal. So a diagram, I think, would then help us in picturing this. So the side length of all four sides here of the square is 5. But when we draw the diagonal, and remember what that diagonal does. It forms a special right triangle for us. It's a 45, 45, 90, which then means we can go from the leg of our 45, 45, 90 to the hypotenuse, which just so happens to be the length of our diagonal. So we multiply by root 2, and that is going to give us the length of our diagonal, so which we'll call d. So we multiply then 5 by root 2, and we end up with then 5 root 2 is the length of our diagonal. So as you can see, knowing the square area postulate comes in handy in finding the areas of squares and also working with some of the properties that we've learned in the past about our special right triangles. Now let's say we want to move on to find another figure's area. Let's move on to find the area of a rectangle. Assume that a pair of adjacent sides measure a length of A and a length of B. Now, so our investigations then turn to how many unit squares can we chop out of this given rectangle if the dimensions of this rectangle are dimensions of A by B. Before we look into actually deriving the area formula of a rectangle, I do want to talk a quick note about the symbolism you're about to see. We're going to be calling the dimensions of a rectangle A by B. So I'm going to give you an A by B rectangle. And so whenever you see this notation of this X between the two values A and B, we don't read that as A times B, but in our case, we'll be reading that as A by B, just simply like the dimensions of the given figure. Um, if you're familiar with any sort of contracting or woodworking information, they usually will give you the length of a board in terms of its dimensions. You may have heard of like a 2x4 or a 1x2 or a 1x4. Those are just simply the dimensions of that board. So this isn't the area formula, but this is saying that this is the given dimensions of the rectangle. And so it's only going to serve us as simply symbolism involved in our derivation of our rectangle. So how do we then go about finding the area of a rectangle given the dimensions of A by B? Let's take a look at our strategy. So our strategy is then to do this. We're going to combine a few figures together. We're going to take two of our A by B rectangles. We're going to take an A by A square, and we're going to take a B by B square, and we're going to fit these pieces together such that we find ourselves forming an entirely larger square. So if we notice with our A by B rectangle, if we extend the side out from one of them, we can form that A by A square, and extending it from the other side, we can form that B by B square. And then using our second A by B rectangle, we attach it to fill it in, thus forming a big square, and that big square is going to help us then find the area of the rectangle that measures that has dimensions of A by B. So we first begin with our area of the A by B rectangles. Let's just simply call these A sub rectangle, meaning that whenever we see this A variable, this capital A, that's simply just going to represent the area of that A by B rectangle, which again, we don't know the area of it, but I just want to let that A represent the area of it. And again, we have this A by A sub rectangle area for our A by B rectangle. Now, we also know, though, from our square area postulate, what the areas of our A by A and B by B squares are. And A by A simply has an area of A squared, and the B by B has an area of B squared. Now we're going to use this information, and we're going to fill in some information off to the right here that's going to lead us into our derivation of the formula. So let's talk about the area first of the big square, right? If we take a look, it is actually a square. All four sides measure the exact same. It is A plus B. And since we actually created it using rectangles and squares, we know that all four angles then are also right angles, so thus satisfying the definition of square. So we have this side length of our square, of our big square, equaling A plus B. Well, our square area postulate then says we know what the area of the big square is. It's simply going to then be the square of the side length. So we have then the sum, A plus B, raised to the power of 2. And that's our first part of our derivation, is to use this a plus b squared, which we'll actually work that out here in just a moment. Then we look at the sum of our subregions. So the sum of our subregions is simply just the sum of adding all four of those parts together. This is using the area addition postulate. So the sum of our four subregions looks like this. We actually have two of those A subrectangle regions plus the area of our first square, which is that A squared region, and then we add in the B squared, the area of our second square there, the B squared area. Now remember, the sum of the subregions adds up to the whole. Well, if we know the whole area of this square, is A plus B squared, then those four subregions, the two rectangles and the A by A square and the B by B square, must add up to that the big square area, the A plus B squared. So now let's use these parts and let's derive the area formula of our rectangle. So we bring these two parts together. This A plus B squared, the quantity of A plus B squared, equals 2 times A, which is the area of that rectangle, plus A squared plus B squared, where A is the area of the original A by B rectangle. We're going to solve for A. So let's bring our equation down here and let's work through some of the algebra here that's going to be used to help us derive the area of this given rectangle. Actually, you know what? I am going to flip the equation around just so we end up with the area A on the left-hand side like we typically see in a derivation formula. So I'm going to put 2A plus A squared plus B squared on the left and move my A plus B the squared to the right, and we'll end up with the result we're looking for. So we begin on the right hand side because there's really nothing that we can do on the left hand side except just wait to see what unfolds as we take this A plus B squared. Now remember, A plus B squared is really A plus B times A plus B, which means we have to do binomial distribution. So we do A times A, which gives us A squared. We do an A times B, and then another A times B, which means we'll end up with 2A times B's, and then we do a B times B, which gives us B squared. Now look at how the magic unfolds as we work out the right-hand side. We begin to see terms that appear on the right-hand side that are also on the left-hand side. So we cancel out our A squareds. We subtract A squared on both sides. We can cancel out our B squared. Those cancel out from both sides. And we're left then with this remaining information, 2 times the area, right? Because there are 2 of those A by B rectangles, is equal to 2 times A times B, which is the product of A and B. Well, we can divide by 2 on both sides, and we end up with our area formula. Looky there, that the area of our rectangle is then simply the product of its dimensions, A times B. Not right. We don't read that as A by B. We only read A by B when we see that symbolism of X between it. This doesn't have that symbolism, which means this really is a product. It really is just A times B. So our conclusion to our area form of rectangle is simply that we can find the area of a rectangle of dimensions A by B by taking those two dimensions and finding the product of A and B. So we end up with A times B is the area formula of a rectangle. So you may have known the area form of rectangle, but now you actually get to see the proof behind why we know the area form of rectangle is simply the product of its dimensions. So we move into our last set of examples, actually finding the area of rectangles using our new area formula. So let's do our first example here. A rectangle has a pair of sides of length 12 and a pair of sides of length 6. Find its area. Let's go ahead and draw a picture. So we have a pair of sides of length 6, pair of sides of length 12, and that means we really do have our dimensions of the rectangle. So we just simply, to find the area, take our dimensions and find the product of those two dimensions. So we're going to do 12 times 6, which then ends up giving us 72. And again, units are arbitrary. So there is the area of our rectangle. That means it took 72 of those unit squares to cover that without gap or overlap. Let's look at our second example here. A rectangle has a diagonal of length 12 and a pair of sides of length 6. So let's again draw a diagram here with our pair of sides of length 6, but this time we have a diagonal of length 12. Now I can't just again do 12 times 6 here, but this 12 is not the dimension of the rectangle. I need to know the other side of the rectangle here. So how do I find that? Well, think about the angles of a rectangle. That's a right angle, which means I have two sides. 6 is a leg of that right triangle. 12 is the hypotenuse of that right triangle. We can use Pythagorean theorem. So I'm going to save us a little bit of time, but we're going to do basically do 12 squared minus 6 squared and solve, and then take the square root of that. We end up getting ourselves, for the length of x, we get ourselves 6 root 3, which is then our dimension we're looking for to find the area of this rectangle, because now we can find the area by simply doing 6 times 6 root 3, which then we multiply our outside numbers together, and we get 36 root 3. So for the most part, on many of the examples you'll find on your homework assignment, you're going to be able to give me an exact answer back. Okay. However, let's take a look at our last example here. There are going to be just a couple examples on your homework assignment where you can't give me an exact answer, only because the nature of the information given to us is not going to enable us to give us that exact answer. Because in this case here, let's say I give you a rectangle such that there is a diagonal that creates an acute angle measure of 36 degrees, and you're given that one dimension of your rectangle has a length of 4. How do we then find out what the other dimension is? Well, if we're given the acute angle measure of that right triangle, we're going to have to use SOHCAHTOA. So using trigonometry, we're going to run into a non-exact answer, an approximation instead. So you'll see that there are a couple problems in which you're going to have to round your answers and give me an approximation. So again, our goal is to find our second dimension of this rectangle. We have our first dimension, 4. We need our second dimension, x. So let's solve for x. There is a function, a trigonometric function, that uses the acute angle there, 36, to relate 4 and x, and that is going to be our tangent function because the sides are opposite and adjacent. So tangent of our angle, 36 degrees, is equal to the opposite, 4, over the adjacent side, x. We're going to solve for x. I'm going to go ahead and do my little switcheroo technique, which is to bring the tangent of 36 and the x, switch them around, which then leaves me with x equals 4 over the tangent of 36 degrees. Now, if we then take a look at our table or use our calculator, the tangent of 36 degrees turns into 0.7265. And then we can evaluate that to get our approximation for the length of x. So we're going to approximate the length of x to be about 5.5, I'll go a few decimal places here, 058. Now keep in mind, we're not finished. All you did was you did a lot of legwork to find the second dimension. So now that you have that second dimension, we can then find the area of our rectangle by taking that dimension 5.5058 times the second dimension that we were actually given, times 4, and we get an approximation of our area to be about 22.0232, and I'll go to the nearest hundredths place on that one, so I'll round that a little bit further to 22.02 is our approximate area of that rectangle. So again, only a small portion of the rectangles on your assignment will you not be able to give me an exact answer. You're going to have to give me an approximation such as this one. However, most of them, you will be able to give me an exact answer. Okay, we've come to the end of our lesson on the square and rectangle area. Please be sure to take a look at that 11-point worksheet. If 11.1 worksheet, if you do have any questions on that homework assignment, please do not hesitate to email me. With that, be good and do good.